This is lesson 58 for geometry, tangents and circles, part 1. So I'm going to get started with a theorem. But first I want to tell you that a tangent line, it lies in the same plane as the circle, and it's going to intersect the circle at just one point, just exactly one point. Okay, so theorem 5-8 kind of explains it. It says if a line is tangent to a circle, then the line is perpendicular to a radius drawn to the point of tangency. So if you have a circle and there's a line that is right here at one point on the circle, like this one is on point G, and then the line only touches the circle at one point, this line is going to be perpendicular to the radius. So you can say that segment DG is perpendicular to segment EF. And we're going to use that theorem to solve some questions. Our first example says line N is tangent to circle C at point P, and line M passes through C. Lines N and M intersect at point Q. First question, they say sketch circle C. Well, we can sketch circle C. That's pretty simple. Just a circle where C is the middle of the circle. And lines N and M. Then mark C, P, and Q on your sketch. So let's read this back. Line N is tangent to circle C. So let's draw a radius. Goes from the center of the circle to the side of the circle. And a tangent line is going to touch the circle at one point. So I'm going to draw it like this. You know what? I'm going to wait a second. It says line M passes through C. This line right here passes through C. So let's draw line M first. We already have for the radius to here. Let's draw a line through it, and this is going to be line M. I'm going to label it. We have point C right here. And then it also says right here that lines N and M intersect at point Q. They cross each other at some point, and that point is Q. So we're going to also have another point on this line because we want line M and N to intersect each other. They're going to cross. So let's draw another line up here, or I'm sorry, another point up here, point P. And these guys, these two lines are going to intersect, not on the circle, because tangent lines do only touch one point on the circle. This is the tangent line that we're going to draw, N, because it says that N, line N, is tangent to circle C. It's only going to touch, a tangent line only touches one point on a circle. So line N is right here, and it's tangent to circle C at point P. And then it says that line M passes through C, so right through the center of C, and lines M and N intersect. Wherever they cross, this right here is going to be point Q. So we have our picture drawn. It says if the measure of angle CQP, this is the angle, if that angle equals 36 degrees, then determine the measure of angle PCQ. PCQ. We got to figure out what this angle is right here, okay? Now, let's look at our drawing right here. This is a line, a straight line. There are 180 degrees on a line, but we're not going to worry about that because we'd have to know what this angle P is to be able to figure that out. We're going to look back at our theorem. It says if a line is tangent to the circle, then the line is perpendicular to the radius. Okay, so this line right here is tangent to the circle. So it means that this line right here, CP, is perpendicular to the radius. Okay, so that means that line CP is going to be a straight line and it's going to be perpendicular. So if you were to add up the angles CPQ, this angle right here, and the angle PCQ, so these two angles, if you were to add them together, they equal 96 degrees. So I'm going to write an equation down for you. If we were to add angle CQP together and angle PCQ, then they add up to 90 degrees. Well, it tells us what angle CQP is. We can replace this right here with 36 degrees. And we'll be able to solve for this angle by subtracting 36 from both sides. So this angle, PCQ, is equal to 90 minus 36, which is 54 degrees. Let's move on to our next theorem. Theorem 58-2. It says if a line in the plane of a circle is perpendicular to a radius at its end point on the circle, then the line is tangent to the circle. So here's a circle. If we have a line, in this case line ST, then this line is going to be perpendicular to the radius. Okay, this line ST is going to be tangent to circle V. It kind of sounds like you're saying the same thing as our last theorem. We're just saying it opposite ways. So forwards, backwards, and backwards, forwards. Our next example says if the measure of angle BEA is 45 degrees, show that line BD is tangent to circle C. So BEA, this angle right here is 45 degrees. Okay, we know that angle's 45 degrees. We have to show that this line right here, BD, is tangent to circle C. Well, using our theorem, we can kind of figure out these angles. This one tells us it's 90 degrees. That means angle A and angle E, these two guys are going to be, if you add them together, they're going to equal 90 degrees. Let's see if we can figure out what each of those are. If you've worked with reference triangles, you're going to know it's 45 degrees, but let's see if we can figure that out by what they gave us. They told us angle BEA is 45 degrees. Well, this guy and this guy are perpendicular. So that means that this whole angle right here, from here to here, is going to be 90 degrees. We already know that this BEA angle is 45, so we can do 90 minus 45 degrees, and that's going to tell us what this angle is, angle CEA. 90 minus 45 is 45, so the measure of angle CEA is 45 degrees. That means that this angle is 45 degrees, but we need to show that this is tangent, and the way we can do that is because this is a 90-degree angle, 45 and 45. In our last theorem, 58-2, it says that if a line is perpendicular to the radius, this line is perpendicular to the radius because we've got a 90-degree angle, then the line is tangent to the circle. So we proved that BD is tangent to circle C, meaning it only touches circle C at one point. And we did that because we found out that this line is perpendicular to the radius. Okay, so we use theorem 58-2. All right, let's move to our next theorem, theorem 58-3. It says if two tangent segments are drawn to a circle from the same exterior point, then they are congruent. So here is the center of our circle, and we have two segments right here that are tangent because they're called tangent because they only touch the circle at one point. So QM and segment D, I don't have a letter there, DN. These two touch the circle at one point. So these two sides, these lines or segments, are congruent. So it means that they're going to equal each other. You can do this on it if you want. Let's look at the next example. It says in this figure right here, JK, segment JK, and segment JM are tangent to this circle. And we can see that by the drawing. JK only touches at one point in the circle, so does JM. Next, it says determine the perimeter of the quadrilateral JKLM. So this shape right here, they want us to determine the perimeter. I'm going to draw it in red. This is the shape. So to find the perimeter of a shape or a quadrilateral, you add all of the sides together, all the outside. So these two, JK and JM, these two segments are congruent, meaning they're going to be the same length. So JK and JM are both 17 inches. It also, right here, from L to M, this segment is 8 inches, and this is a radius. LK is also a radius. That means they're going to be the same length. So segment LK is also 8 inches. So if we want to find the perimeter, we add all of the sides together. 17, you can do 17 times 2, or 17 plus 17 plus 8 plus 8. If you add all of those sides together, you're going to get 50 inches. Don't forget your units. Now it asks you what type of shape or what type of quadrilateral is quadrilateral JKLM. So it has two congruent sides here, and these sides are also congruent. Because it has two pairs of congruent sides, then it's a kite. And you can kind of see by the shape, it looks like a kite. All right, our last example is example 5. It says an ornamental window has several glass panes, and this is the drawing. An ornamental window has several glass panes oriented to look like an eye. The radius of the eye's iris is 3 feet, so the radius is 3 feet. And segment DC, from here to here, is 5 feet. We want to find out what segment AI is and segment AH. Well, just by using our theorem 58-3, we know that these two lines, AH and AI, are tangents to this circle. They only touch at one point on the circle, so they're going to be congruent. We don't have a number yet for them, but we do know that they're going to be congruent. We know the radius here, this side down here. So what you can do is you can draw a line from A to F. We're going to cut this quadrilateral down the center. So this right here, we'll have to see if we can find the length of AF. Well, if you look right up here, it tells us that segment DC is 5. This is the same distance. A to F is the same distance as D to C. So this is 5. So we have right triangles here and right triangles here. We're going to be able to solve this, okay? We can find that we have two triangles, FAI and FAH. The hypotenuse right here is 5 feet long. This is in feet, it tells us feet. So this hypotenuse is 5 feet long. And the shorter legs, this is 3. This is also 3 because it's a radius. These are all HF, IF, and these lines right here are a radius. So they're going to be congruent 3. Now we can use Pythagorean theorem and we can solve for AI and AH. So Pythagorean theorem, if you solve this, you're going to find out the length. So if we want to find this side right here, you can always rewrite one of the triangles, but I'm going to redraw it for you here. I'm going to redraw this one. This right here, this side is 5, this side is 3. We have I, F, and A. We're trying to find out what this side is right here. Okay, so My triangle's not perfect, okay? To solve for this, we're gonna use Pythagorean theorem. A squared plus B squared equals C squared. The hypotenuse right here, this is the hypotenuse, so that's gonna be 5. And then you can use 3 in place of A or B, it doesn't matter. Okay, let's solve this. A squared plus 9 equals 25. Subtract 9 from both sides. We have A squared equals 25 minus 9, which is 16. To get rid of this square, you do the opposite. You take the square root of both sides. So A equals, the answer is plus or minus 16, but we're not going to have a negative length. So it's going to be, I'm sorry, plus or minus 4. But since we have a side here, it's not going to be a negative length. So 4 is our answer. We have 4 feet from AI and AH. They're the same, so they're going to be 4 feet. Your homework tonight is lesson 58 on page 384, letters A through E.